All right, welcome to part 7 of Multidimensional Essentials. We are going to dive even deeper into the shape of space. And once again, talking to our friend Arthur Loeb, who was a collaborator with Buckminster Fuller and with M.C. Escher. I mean, when you're talking about the shape of space, who knew more about it than M.C. Escher, right? Like, to make the art that he made, like how must have his brain been organizing his understanding of space and time? So Arthur Loeb, in his book, Space Structures, says space is not a passive vacuum, but has properties that impose powerful constraints upon it, any structure that inhabits it. So these constraints are independent of any specific interactive forces, hence geometrical in nature. So our interactive forces are things like time, gravity, friction, momentum, angular momentum, all these different forces. And Amy Edmondson, who wrote the book A Fuller Explanation, which is like the study guide to Buckminster Fuller's epic work Synergetics. And Synergetics is really the foundational text for everything we're talking about here. And so grateful to Edmondson for putting into layman's terms a little bit. And she says, nature's structuring occurs according to the requirements of minimum energy, which is itself a function of the interplay between physical forces and spatial constraints. Nature's structuring occurs according to the requirements of minimum energy. And this is an interplay between physical forces and spatial constraints. So we've done a pretty good job so far of identifying and defining our spatial constraints. And in order to get into how nature actually works, we need to bring in the physical forces, time, gravity, these sorts of things, right? So the geometry we've looked at so far is purely abstract, right? Strictly metaphysical, independent of size, gravity, and time, right? You can take a tetrahedron in the abstract and expand it. It doesn't matter if the tetrahedron is 1,000 miles wide or, you know, the tiniest millimeter wide. It's the same structure, the same set of relationships. But once you start bringing in things like weight, density, time, movement, angular momentum, all of a sudden we're dealing with a much different thing. And our friend Buckminster Fuller, I just love this photo of him, just having a great time playing with it's called a buckyball. And it's a model. There is an element called Buckminster Fullerene, and it's got to do with the 64 tetrahedra, that is the vector equilibrium, which we're going to talk about now. Anyway, he was nothing if not practical, right? He developed all this sort of theoretical stuff based on very concrete observations. There are stories of him getting in trouble at school as a young one, annoying all his teachers with protestations about how can a two-dimensional surface be created by placing lines next to each other if the line, like we said, the line has no width, right? The line doesn't have any width side to side or up and down. So how can you take something that has no width and start and place a bunch of them side to side and then create a plane? It doesn't make sense. And same with stacking. Okay, so you've got a flat plane that has no verticality, and then you stack a bunch of them together, and all of a sudden you've created space. Like, does not compute. That doesn't actually make sense, except in this very abstract way. And so his teachers used to get mad at him, like, you're not being serious, young man. Like, you're undermining the lesson, right? And so Fuller believed that mathematics, which is the science of structure and pattern, should be based on the principle that the shape of space is fundamental to the events of nature. The things that we can actually observe and experience around us are happening because of the shape of space. And that's what mathematics should be about, figuring out what's actually happening. How do we explain our own experience? And Fuller insists that synergetics originates in the assumption that dimension must be physical, so must have size. So if we're talking about multiple dimensions, we can't actually just stay in the metaphysical realm. We have to get into the concrete, into the physical. And the fact is, there is no dimension without time. There is no dimension without time. So to make all of this practically applicable, which is what we really want to do from now on, is we must admit that there are specific interactive forces that have a role to play. Life is not strictly geometrical. Life is messy, full of these pulsative asymmetries. So what do we do? What do we do? Well, first, let's remember that Euler helped us determine that any shape can be defined by the combination of vertices, edges, and faces, plus 2 for the innate polarity of existence, right? This is Euler's law. And so growing through the dimensions, just to review, we went from dots, which is the first vertex, right? A dot we can think of as a vertex, everything coming to meet at that dot. We went from a dot to a line. A line is the same as an edge. From a line, we went to two-dimensional polygons, right? Faces. The polygons are the two-dimensional shapes, which we know as the faces. And then we took faces and created 3D polyhedra. Just to clarify the difference between a polygon and a polyhedra, the polyhedra is the three-dimensional container of space, and the unit of measurement for that is called a cell. And so we got vertices, edges, and faces, all of which combine to create a cell. Now, the natural next step is to add the natural forces of time, gravity, angular momentum, which is spin, electricity, and magnetism into the creation to see how that structure holds the actual forces which move life along. Now, Edmondson says, by viewing polyhedra as vector diagrams, Fuller makes a deliberate attempt to develop one comprehensive format to accommodate both the inherent shape of space and the behavior of physical phenomena. Thus, we have vector polyhedra. This is an integration of the static concepts of geometry, which we've been focusing on thus far, with energetic reality. The basic function here is to replace edges with vectors. And so let's talk about what is a vector. Vectors provide an ideal tool for representing velocity, force, and other energetic phenomena. As you may recall from high school physics, the concept is pretty simple. It's a line with an arrow. And so the length of the line determines magnitude, and the direction of the arrow determines direction. And this is how we measure force, right? Magnitude and direction. It's the ultimate simplification of actions or forces to the most relevant bits of information. And the mechanism as a whole enables us to predict the results of complex interactions of forces and bodies in motion, right? Again, high school physics. If you can think of all the different forces and measure, okay, this vector is going that way, this vector is going that way, this vector is going that way and that way, then you can make an accurate prediction of how a body in motion is going to respond. Yeah, it's how we do car crash testing and launch things into space. We basically just do the math with different vectors, calculate for all the different forces involved, see how they interact, and that is how physics works. So what we want to do at this point is integrate vectors into our spatial structures. And is that making sense so far with me? That's coming together? Okay. So surveying classical geometry, Fuller realized there's nothing to identify time. And he says, there's nothing to identify time, and nature has time. So I'd like to get that in there, and so vectors seem to have the solution. And he says, I like vectors. A vector represents a real event of nature. I wondered if I couldn't draw up a geometry of vectors. That would mean having the elements of experience, and the elements of experience encoded into our metaphysical realm is really what we want to get to. So integrating the real forces of life in the form of vectors into our geometrical exploration leads quickly and inevitably to a new shape with intriguing qualities. So far we've really focused on the 5 Platonic solids. And of course, there are many, many beautiful, wonderful, interesting shapes out there, but those 5 are really special. And then this one is also of great importance that we want to know about. And that the geometrical name for it is the cube octahedron. And it is more famously known as the vector equilibrium, or VE for short. The vector equilibrium is the cube octahedron. So you can tell just by the name that it's some combination of the cube and the octahedron. And isn't it interesting? Those two are the paired opposites of earth and air, right? And you wind those together and start working with vectors, and it creates the only possible shape, which is a vector equilibrium. We talked about how there's only 5 shapes that satisfy the rules of the Platonic solids. There's only one shape in all of possible existence that satisfies the requirements of the vector equilibrium, which Fuller, with typical flourish and vocabulary, describes as, he says, the vector equilibrium is an omnidirectional equilibrium of forces in which the magnitude of its explosive potentials is exactly matched by the strength of its external cohering bonds. An omnidirectional equilibrium, equilibrium in every direction, in which the magnitude of its explosive potential, so that all the things that make it want to explode out into space, are perfectly counterbalanced by the strength of its cohering bonds, all the things that are keeping it together. Okay, so we defined a vector. Let's talk about equilibrium for a moment. We got a vector equilibrium. We know what a vector is. What's equilibrium? And so Edmondson tells us that defined by the American Heritage Dictionary, equilibrium is any condition in which all acting influences are canceled by others. This results in a stable, balanced, or unchanging system. And the key point here is that equilibrium is not inactivity. Right? We've been looking at geometric shapes that have the quality of inactivity. And what's so interesting about equilibrium is it's not inactivity. It is it's a dynamic balance. There's a force this way and a force this way, and they just happen to be perfectly counterbalanced. That's equilibrium. And Edmondson points out that this balance is not necessarily physical, but may be mental or emotional as well. In fact, so much of our experience is characterized by fluctuation in and out of fragile balances that it is easy to understand the word's frequent use covering everything from structural to emotional to financial equilibrium. And we're gonna spend more time on this in section 10, but that balance of equilibrium is such a crucial thing. We talk about it in Ayurveda all the time, and in every realm of life we can think about this delicate balance. And this is where the pulsative asymmetries come in again, right? Because it's not inactivity, and you may only reach equilibrium for a split second. It's like, oh, I did it. Oh, now I'm tipping this way. Oh, now I'm back this way. Oh, I did it. Oh, now I'm back this way, right? And it is this dynamic balance of forces. So we're looking at the geometric basis for that. Okay, let's watch some videos.